welcome to the Bodhi Academy. My name is Amja Klasso, and in today's video we will continue with our class 12 chapter 2 electrochemistry. So previously in this chapter we learned about the Nernst equation, how to write the Nernst equation, and then we also saw its two application, that is one is with reference to equilibrium constant and one was with reference to Gibbs free energy. Now look at this table. So this is the standard electrode potentials of all these metals, different metals which are there, and their values are given here. So in last class when we discussed something about the negative values and the positive values. So if you look here from Pb, that is lead, if you look, the values are turning into negative. So what we said about negative values, that these values, if they are negative, they say that the reduced state of these metals are less stable than that of hydrogen gas which is present. And if you look at these positive values, we have where we have fluorine F2 and it goes up till hydrogen, or last we have AgBr silver bromide. So in this case these all have a positive value which indicates that their reduced state is more stable than that of the hydrogen gas that is present. Now in today's class we will start with a new topic of conductance of electrolytic solutions. Now to understand this, let's first understand the difference between conductance and resistance. Let's begin by understanding resistance first. What is resistance? Resistance is basically the ability to resist the flow of current, okay, and conductance is basically right the opposite of resistance. So it is the ability to conduct current. So in resistance it is denoted by capital R. Its unit is ohms and it is given by an equation that says R equals to rho L upon A. L is the length of the conductor and A is the area of cross section. Now in this case what you see is that resistance here is directly proportional to the length of the conductor. You see this is R is directly proportional to length of the conductor and R is inversely proportional to area of cross section, okay, and rho which is given, that is the resistivity, or it is also known as specific resistance. Now if you have to write about conductance with reference to resistance, you have to write the opposite of resistance. So conductance is what? It is the ability to conduct and it is denoted by the alphabet G. Now its unit is, if this is ohm, this will be ohm inverse, and same way it has a unit called mho, MHO. Even the words are reversed over here. Now G equals to, the formula is G equals to 1 upon rho Ka upon L. So in this case again the formula is reversed. So rho is taken now here as inverse, and here it was for resistance, it was length by area, here it is area by length. Now this inverse that is there, 1 upon rho, it is denoted by a constant called K, that is known as kappa. So that you have to replace here. So G equals to K A upon L. So now in conductance what we see? Conductance is directly proportional to area and conductance is inversely proportional to length, okay. Now substances, every substance is classified into three categories, okay, three major categories. First one is the conductors. Conductors are the ones which have a very large conductivity. Example is metals and alloys. Alloys are mixtures of two metals, so therefore both are large, both have large conductivity. Next we have the insulators. Now insulators, they do not conduct electricity. Examples would be glass and ceramics. Semiconductors are the ones that basically fall between conductors and insulators. Their conductivity ranges from insulators to conductors, okay. So one example would be silicon and another would be gallium arsenide. Now there is also another category that is not very known but it exists, that is the superconductors. Now in superconductors its property is that it has zero resistivity. Okay, so if something has zero resistivity, we say that resistance and conductance are inversely proportional or they are opposite, correct? So if something has zero resistivity, what can we say about its conductivity is that it is infinite. Example would be ceramic materials and mixed oxides. Now let's understand what is metallic or electronic conductance. Now say here electrical conductance through metals is called as electronic conductance, and this is due to movement of electrons. So any conductance or any electrical conductance through any form of metal, that is called as metallic or electronic conductance, and this is majorly happening due to flow of electrons. Now electrical conductance through metals is called metallic or electronic conductance, and it is due to movement of electrons. The electronic conductance, it depends on three major factors. First is nature and the structure of the metal. How is the nature of the metal and what is its structure? So then we have the number of valence electrons per atom, because these are the electrons that are going to travel, correct? And we have lastly the temperature, which tells us it decreases with increase of temperature. So electrical conductance in metals, it decreases as we increase the temperature. Now next, if you look at pure water, okay, pure water is said to have very low conductivity. Now if you say pure water, what does it mean? That its ion concentration of hydrogen and hydroxyl ions is comparatively very less. That is the reason why it is having very low conductivity. Now to the same water, if you say you add some electrolyte, in that case what will happen? It will furnish the the ions in it, and therefore what will happen? The conductivity of the water will increase. So this conductance of electricity by ions present in the solution is called as electrolytic or ionic conductance. Okay, so now this again depends on five major factors. First is again the nature of the electrolyte that is being added, what kind of solution you are adding, that also matters. Then the size of ions produced and their solvation, how easily they dissolve and how easily they are able to dissociate into the solution. The nature of solvent and its viscosity. Then the concentration of electrolyte, how much of electrolyte you are adding, because based on the concentration the number of ions present will be dissociating. Therefore concentration of electrolyte is also a very important factor. And lastly we have temperature, which says the ionic conductance, it increases with increasing temperature. So ionic conductance here is directly proportional to temperature. If one increases, the other also tends to increase. Now let's see how is the measurement of these conductivity of ionic solutions is done. So usually unknown resistance, it is measured by the Wheatstone bridge. But now in this case we face two major problems. Okay, first is when you pass direct current, that is DC, that changes the composition of the solution. And if it means that if the composition of the solution is changing, as in some more extra ions are being added, and therefore the conductivity will also vary. Second is a solution cannot be connected to the bridge like a metallic wire or other solid conductor. So to overcome these two problems, first solution for the first problem was given that the first difficulty is resolved by using an alternating current AC source of power. So instead of passing a DC current, that is a direct current, you pass a AC current, that is a alternating current. Second is a specially designed vessel called conductivity cell is used instead, because you cannot connect the bridge like a metallic wire or other solid conductors directly to the solution. In that case what we do is we have a specially designed vessel called as the conductivity cell. Now let's look at this conductivity cell. Now there are two types, there are several designs, but here they have given two designs of this conductivity cells. So basically it has a platinized platinum electrode, two platinized platinum electrode and a connecting wire. Same way here also they have two platinized platinum electrode with respective connecting wires. So basically it consists of two platinum electrodes that are coated with platinum black, that is finely divided platinum is deposited on the electrodes, that is electrochemically. These have a cross area section equal to A. So area is area of cross section, and they have a length as in this length, the length by which they are separated. Okay, it is this length that is calculated, separated by a distance L. Therefore, the solution confined between these two electrodes is a column of length L and the area of cross section A. So the resistance of such a column solution, it can be given by this equation that we already know. Resistance equals to rho L upon A. This rho, if you substitute, we know rho is what? So this rho, if you take it as rho is, we know it is 1 upon K. Okay, so this, in previous case what we saw, K is 1 upon rho. So rho can be substituted, you get this here, and you get 1 upon rho here. So that 1 upon K you can substitute here, correct? So you get length upon Ka. Now the quantity La which is there, that is length upon area, it is called the cell constant. Okay, so length upon area which is there, L by A, this quantity is called as the cell constant, and it is denoted by G star. Okay, now this depends on the distance between the electrodes and the area of cross section, and has a dimension of length inverse and can be calculated if we know length and area. So the measurement of L and A is not only inconvenient, but it is also unreliable. Now in this case what will happen? See, if I take this one and this one, in this case the distance between the two platinum electrodes is very less, but if you look here, the distance is like very much extra than it was in this case. So on this makes it a very unreliable source for the measurement. So therefore the cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. So in this case what we do, because of this unreliability, what we do is that the cell constant that we have to calculate, we measure it by using a solution whose conductivity is already known. Okay, now for this purpose we generally use a solution of KCl whose conductivity it is already known at various concentrations and at different temperatures. So the cell constant G star is given by the equation. So you can write it as G star equals to L upon A equals to RK. So now in this column we have the different concentrations. Okay, they have the different concentrations, and we have the respective cell constants that are present. Now once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. So once now we know the cell constant, our major part is done of finding the cell constant. Now you can directly go down to understand what is, or to find out what is the resistance or conductivity of any solution. The setup for measurement of resistance is shown in figure 2.5. So this is the figure. Over here you have the detector, we have the conductivity cell, and we have the resistors. It consists of two resistance, that is R3 and R4, and a variable resistance, that is R1. As in this resistance can be changed, this remains fixed, and the conductivity cell having a known resistance R2. So the resistance of this conductivity cell, that is that R2, is known to us. The Wheatstone bridge is fed by an oscillator O. It is fed by a oscillator O. P is a suitable detector. Here this is the oscillator. This is the setup of the Wheatstone bridge. This is the oscillator, and here we have the P, that is the detector. So P is a suitable detector, and the bridge is balanced when no current passes through the detector. Under these conditions we have, so basically it is like we have R3, R2 equals to R1, R4. This is the equation. Now to find the unknown resistance of R2, if you want to find, so what we do is that R2, R1, R4 upon R3. Okay, so this equation is known. Now these days we have many inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. So nowadays we have ample number of conductometers which are present. These conductometers, what they do, they basically directly you insert the electrodes into the solution you want to find out the conductance of, and they directly give you the value of the conductance that is present. Now once the cell constant and the resistance of a solution in the cell is determined, then the conductivity of the solution is given by the equation K, that is kappa, equals to cell constant upon R, that is G star upon R. So the conductivity of a solution of different electrolytes in the same solvent and at a given temperature, it differs due to charge and size of the ions in which they dissociate. So one major we learned even in ionic conductance, that it majorly depends on the size and the charge that is present on the ions and how they will dissociate. Now the another important factor I told there was concentration of ions or ease with which the ions move under a potential gradient. So therefore it becomes necessary for us to define another meaningful quantity that is known as the molar conductivity. So molar conductivity, it is denoted by a Greek symbol lambda m. So it is related, this lambda m denotes the molar conductivity. It is related to the conductivity of the solution by this equation. So molar conductivity, that is lambda m, equals to K, that is kappa upon C. Now in the above equation, if say K is expressed in Siemens meter inverse and the concentration C that is there, it is given in mole meter minus 3, then the units of lambda m are in Siemens meter square mole inverse. Now it may be noted that 1 mole meter minus cube equals to 1000 liter per mole cube. So into molarity, that is there, mole into liters, and hence what we get here is, after substituting all of them, if we use Siemens centimeter inverse as the units for K and mole centimeter cube the units of concentration, then the units of lambda m are S centimeter square mole inverse. Now it can be calculated by using this final equation that we get, that is K into 1000 upon the molarity of the solution that is given. Now both types of units are used in literature and are related to each other by the following these two equations. So you can use any type of units, both have a related relation that is given in literature. So you can use either this one or this one. Okay, so that was it for today's video. So we learned about what is the difference in conductance and resistance, what are its formulas, then we classified substances into 4 different categories, then also we did about metallic or electronic conductance, understood what is ionic conductance, also learned the factors on which metallic and ionic conductance depend. We learned the measurement of conductivity of ionic solutions. Okay, so that was it for today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.